Hey everybody. Today we're getting started on power series. A power series is basically just a polynomial that could potentially go on forever. This is the most compact way of writing one, sum n equals 0 to infinity, c sub n x to the n. So the cn are just the coefficients of the xn's. Different values of x are going to give you different values here, so we're really defining a function using a power series. Also notice that for some values of x, we expect this series will converge, and others it might diverge. We've already seen at least one example of a power series, the geometric series, sum n equals 0 to infinity of xn. And we know that this converges when the absolute value of x is less than 1, diverges otherwise, and that when it converges, the sum is going to be 1 over 1 minus x. The values of x for which a power series converges is going to define the domain of the function defined by that power series. Makes sense. There's a slightly more general way of writing a power series. Sum n equals 0 to infinity, c sub n, x minus a to the n. We call this a power series centered at a. A power series always converges at its center. If you plug in x equals a into this, all the terms are going to go away except possibly the first, and you're just left with c sub 0. Now the power series could be defined elsewhere, could converge elsewhere. We just have to do some work to figure out where else it might converge. Typically, we do that with the ratio test. Let's use an example to see why that's effective. Sum n equals 0 to infinity, 3 to the n, x to the n. We'd like to know where this series converges. The ratio test says take the ratio of adjacent terms, a sub n plus 1 over a n, take the absolute value, and then look at what happens as n goes to infinity. Plugging in, I get this ratio, 3 to the n plus 1, x to the n plus 1 over 3 to the n, x to the n, and immediately get cancellation. In particular, notice the adjacent terms have x to the n plus 1 and x to the n. And those are going to cancel to give us x. That'll always happen when you do the ratio test on power series. Also, in this case, 3 to the n plus 1 over 3 to the n is just 3. The ratio test says that our original series is going to converge absolutely when this is less than 1. So when 3 times the absolute value of x is less than 1, in other words, when the absolute value of x is less than a third. So from negative a third to positive a third. Additionally, the ratio test says that the series is going to diverge when this limit is greater than 1. So we have to check the endpoints manually. The ratio test says nothing when that limit is exactly 1. Let's plug each one in and see what happens. When x is a third, we get this sum. It's just the sum from n equals 0 to infinity of 1. So 1 plus 1 plus 1 plus 1 and so on. That's going to be infinity. The series diverges when x is a third. Similarly, when x is negative a third, we get the sum from n equals 0 to infinity of negative 1 to the n. And that's going to be 1 minus 1 plus 1 minus 1 plus 1. The partial sums just alternate between 1 and 0. So again, a divergent series. Putting that together with what we learned from the ratio test, we have that this series is going to converge on the interval negative 1 third to positive 1 third. Endpoints not included. Okay, so in this last example, we saw that the power series converged on an interval from negative 1 third to 1 third. And in particular, the center of that interval was also the center of the power series. That's true in general, and that's summarized by this fact. For any power series, sum cn x minus a to the n, there are exactly 3 possibilities. 1, the series converges at the center, x equals a, and nowhere else. 2, the series converges everywhere for all real numbers x. And 3, the power series converges within a radius of that center. To say that a bit more mathematically, it converges for absolute value of x minus a less than r, and diverges for absolute value of x minus a greater than r. The number r in that case is called the radius of convergence. Generalizing that a little bit more, we'll say that in case 1, the radius of convergence is 0, and in case 2, the radius of convergence is infinity. this lets us talk about the radius of convergence for any power series. Again, overall, every power series is going to converge in an interval centered about the center and having a certain radius, capital R. Let's do a couple of examples. Determine the interval of convergence of the sum from n equals 0 to infinity, x to the n over n factorial. So here's the ratio test, limit n to infinity, a sub n plus 1 over a sub n. We're going to do that division by multiplying by the reciprocal, canceling out all those common factors of x, simplifying the factorial, the ratio of the factorials, just to get an n plus 1 on the denominator. Now, regardless of what x is, as n goes to infinity, this thing is going to 0. The denominator is getting large and the numerator is staying the same. Therefore, by the ratio test, this power series is going to converge absolutely for every value of x. The radius of convergence is going to be infinity. Let's do a more complicated example. Sum from n equals 2 to infinity of this big mess. Again, we do a ratio test, plug in n plus 1, divide by the general term an, take absolute values and let the limit go to infinity, n go to infinity. Right away, the factors of negative 1 are going to go away. They're going to get killed by the absolute value. I'm going to do the division again by multiplying by a reciprocal. Now I have an x to the n plus 1 in the numerator and an x to the n in the denominator. There's going to be a lot of cancellation there. I'm just going to be left with a single factor of x, which I'll pull out, keeping the absolute value. I'm also getting a lot of common factors of 5. 5 to the n on top, 5 to the n plus 1 on the bottom. I'm just left with a single factor of 5 in the denominator. Now I have to evaluate the limit to see what happens to this rational expression. So on the top, I have a polynomial of degree 5. In the bottom, I have a polynomial of degree 5, both of them polynomials in n. I could do some L'Hopital's rule on this. I could factor out n to the 5th from the top and bottom and cancel. Proceed that way. I'm going to use a little bit of a shortcut here. I know when I have a limit as n goes to infinity of a ratio of polynomials, only the highest power term in the top and bottom matter. So here I'm left with the limit as n goes to infinity, n to the 5th over 5n to the 5th. And of course I've still got that absolute value of x. So overall I've just got the absolute value of x over 5. By the ratio test, the power series is going to converge absolutely when this is less than 1, and diverge when it's greater than 1. So in other words, it's going to converge for absolute value of x less than 5, and diverge for absolute value of x greater than 5. Once again, I have to check the endpoints manually. I have to see particularly what happens when x is 5 and when x is negative 5. So when I plug in 5, I get 5 to the n on top, 5 to the n on bottom, and those cancel. Now, this series is going to converge by the alternating series test. It's an alternating series because of negative 1 to the n, and the general term goes to 0. Also, the general term is going to be decreasing, at least after a little while, and I can check that, for example, by taking a derivative. When x is negative 5, I have the same series, but it's no longer alternating. I need to determine whether this converges or diverges, and I'm going to do it using the limit comparison test. So I see a degree 2 polynomial over a degree 3 polynomial. My intuition is that this is going to behave basically like the harmonic series, sum of 1 over n, which we know diverges. The limit comparison test says take the general term of each of those two series and take their ratio and see what happens as n goes to infinity. Remember, if I get a positive constant between 0 and infinity, then these two series are going to have the same convergence or divergence. In this case, when I do that ratio, I get n cubed over n cubed minus 2n plus 1. And the limit of that is going to be 1, for example, by applying L'Hopital's rule a few times. Therefore, the two series are either going to converge or diverge together. Since the sum of 1 over n diverges, so does our series. Putting everything together, we have that our original power series converges on the interval from negative 5 to 5, including 5, but not negative 5. And again, the radius of convergence is 5.